Okay, everyone, and despite a bit technical hiccup, we got started this Cape Advanced Technology lecture. And we have the great pleasure as Professor Rami Ghannam from the University of Glasgow to join us. And he's a professor of electronics and the nanoscales at the James Watt School of Engineering at the University of Glasgow. He also serves as convener of postgraduate studies and previously held industrial positions at Nortel Networks and IBM Research GmbH in Germany. His research background includes a PhD in electronic engineering from the University of Cambridge, actually from this division, and as well as an MSc from Imperial College London and a BEng from King's College. He's a fellow of the British Computer Society, a senior member of the IEEE, and principal fellow of RET. He is regional chair of the IEEE Education Society in Scotland and the chair of the IEEE Pedagogy in the Engineering and the Technology Network. Rami Ghannam's research focuses on the developing interactive electronic devices and systems that enhance learning and training. He explores how technology, computer games, and simulations can nurture cognitive skills and promote engineering thinking capabilities. That's again.
Thank you so much. Thank you, David. So, good afternoon, everyone. Thank you very much for the invitation. It's a pleasure to be here. It's been a long time since I was last here. I could recognize some very familiar faces. Obviously, a long time ago. Mike as well. Tim used to tell me off for going into his clean room. Obviously, Professor Daping. So thank you very much. As I said, my journey in Cambridge was started when I was a student at Hills Road Sixth Form College. So that was a very long time. Anybody from Hills Road here? No? Anybody know what Hills Road Sixth Form College is? Yes. Okay. So I must have family members there. But a very nice college. Yeah. So it's but the thing is, since 2006, I don't think I've only been to Cambridge twice. So this is my third visit. So thank you very much, David, for the invitation. So today I'm going to be talking to you a little bit about what we are doing at the University of Glasgow in terms of interactive electronics and how we're linking that to education. And this is something that I'm very keen on, very passionate about lately. So I'll start off just by mentioning a few things. So the talk will be roughly split into two parts. Since most of you are doing liquid crystals research, I started also here in Cambridge doing liquid crystals research. Very nice material to work with, very difficult material to understand. Still, a lot of things to understand about liquid crystals. I did a fair amount of experimental and simulations work at Cambridge, and still we do some of that in Glasgow. And then following on from that, I'll be talking about how we're using some of these interactive technologies where liquid crystals are right at the heart of these technologies. And as well as other things as well that we are doing to promote teaching and enhance learning of difficult and abstract concepts, such as engineering, of course. These are images of some of my group members at the University of Glasgow, and I would really encourage you to visit Glasgow. Weather is just as good as Cambridge. You believe that, you can believe anything. But it's a fantastic place. Glasgow is an ancient university, similar to Cambridge. A lot of history, and there are great people there as well. So I really encourage you to visit Glasgow if you haven't done so already. So Daping's already talked about, very kindly introduced me to yourself, so I won't talk a lot about that, but just want to mention that currently very interested in developing these technologies that have a measurable impact. And here I want to stress the word measurable in the sense that we're using sensors to collect neurophysiological feedback, so feedback from participants to understand how they behave, to understand how they interact in these environments that I'll be discussing. So mainly virtual environments. Okay, so some of the projects, I'm going to be talking a little bit about some of the research that we've done. So some of the projects are on our web pages. They can briefly be lumped or clustered into three main areas: energy harvesting, design for learning, and signal sensing and signal processing. We're going to be talking a little bit about some of the previous research that we've done very quickly, and then go into the core of the presentation. So once upon a time, when I was at this lovely company in Zurich, IBM Research, fantastic place to work for. It was always my dream to work for IBM Research, and I had the pleasure of working with some very clever people there. And during my time at IBM, I was working in the area of photovoltaics. So you might ask, why is IBM working in the area of photovoltaics? There are core businesses in computers and making computers and software. Well, in fact, at the time, IBM was working on how to extract heat from these advanced microprocessors. And what they discovered was the amount of heat that you need to extract from these microprocessors is very similar to the amount of heat you'd need to dissipate and extract, get rid of from concentrated photovoltaic cells. So at the time, this was back in 2008, 2009, so a long time ago, 15 years ago, in fact. Photovoltaic cells were very expensive at the time. Still, even single junction PV cells were quite expensive. And the efficiency of these PV cells was also relatively low. People at the time used to categorize PV cells into first, second, and third generation. In my opinion, I'd like to categorize cells into two main categories, or two main broad categories: crystalline or non-crystalline cells. So crystalline are things like, silicon material-based cells. Anyway, these single junction PV cells, their efficiency at the time was around 15 to 16%, quite low. And as I mentioned, they were quite expensive as well, around $1 per watt, the cell. So we're not talking about the module, we're just talking about the cell. So IBM thought, okay, so what if we could reduce the size of these cells? And instead of having a single junction, and as you know, so you're all very bright people, you know how these PV cells work, right? Single PN junction diode. So you are limited to how much energy can be converted from the sun, obviously, with this single junction. So IBM said, okay, so why don't we try to use materials with different band gaps to absorb as much as possible from the sun's spectrum. And in this case, we could go up from an efficiency of 15 to 16%, the efficiency at the time for a triple junction PV cell to around 37, 38%. And so the idea was, okay, so we've got this triple junction PV cell. It's very expensive. Why don't we use some cheap optics to focus as much as possible, to focus the sun onto this very small area. And by focusing the sun's energy into the small area, we're obviously generating a lot of heat. And so at the time, a group of my colleagues and I, we thought of why not reuse that heat for driving a thermal membrane desalination system. And this was great because usually countries with a lot of sunshine, they also don't have access to a lot of water. So it made, or clean water in that case. So it made sense to develop a system like this, and obviously to license the IP to countries, Sunbelt countries. So moving on, there's a lot of it. I appreciate there's a lot of information on the slide, but I'm happy to, to answer questions and discuss later on. I'm just letting you know about some of the stuff that we've done. So we've moved from these large-scale systems to smaller scale systems, and we thought, returned to the UK, The UK has a wealth of sunshine, as you know. And so instead of harvesting energy from the sun here in the UK, we thought, why don't we try to power electronic devices using these tiny PV cells? And at the time, we were considering implanting these PV cells underneath the skin. So we did a bit of research around where we could implant the PV cell underneath the skin. So there was a fair amount of optimization going on there in terms of modeling, big advocates of modeling and simulations, obviously experimentally verified models. And then we looked into developing or fabricating these PV cells using the CMOS fabrication process. So this was the 65 nanometer CMOS fabrication process. You could see this is a single PV cell, which again, following on from the multi-chip module that you've just seen previously for a large scale system. So this is for a smaller scale system. And then we looked into what kind of configuration of these PV cells would enable us to generate a lot of energy, or as much energy as possible. And we could go up to efficiencies of around 18–19% using these PV cells. And as you know, underneath the skin, there's a lot of light attenuation, and this is problematic as well. So it was important for us to optimize the structure of the PV cell so that we could design it in a way to convert maybe red wavelengths of light. So, and as you know, in a silicon PV cell, red isn't exactly a very good wavelength to work with silicon, because it's usually almost transparent. You know, if you're aware, sure you are aware of the absorption coefficient of silicon, and that longer wavelengths than these wavelengths, they just pass through the material. So it's important for us to optimize the material accordingly. And in terms of the configuration of the PV cells, then we found that highest, or the maximum amount of power, was generated when we arranged the PV cells in this format, a 1/6 format, where the cells are obviously placed in series. We did a bit of work on gesture recognition. So this was actually this was a bachelor student work, very interesting work, where we looked into gesture recognition. So here, these are conversion capacitive sensors that were placed on a simple PDMS wristband. And back in 2009, when there wasn't this plethora of work around AI, we were looking into how we could recognize a person's gestures using some very simple capacitive sensors, okay, that were placed around the wrist. And we can classify, at the time, I believe it was 4 or 5 gestures at a very high accuracy. We then thought, okay, so let's extend that work a little bit further. We went on to use pressure sensors. So instead, again, commercial pressure sensors, but instead of using just simple pressure sensors and some machine learning algorithms, so SVM algorithms, to classify these gestures, we combined these sensors with radar in order to more accurately classify the gestures. And in this case, we were able to classify a larger number of gestures, I believe up to 20 gestures, using this technique. Okay, and some of the results that the group generated. Okay, so instead of using these commercial sensors, we thought, why don't we fabricate our own sensors? And here, this is some of the research that we were doing with other types of sensors. These are RGO, reduced graphene oxide sensors. So as you know, graphene is a great material, but its performance can be enhanced using things like silver nanowires. Silver nanowires and mechanical properties aren't so great. So in summary, we tried to improve these properties using PS nanospheres, polystyrene nanospheres. And here, instead of just hand gestures, we also looked into characterizing voice gestures as well. Okay. So some of the work that we did in this area, and some images from our clean rooms about this work, and further details available below as well. So all kinds of gesture recognition. So hand gesture recognition, voice gesture recognition, also eye gesture recognition. So here we were using TMR, tunneling magnetoresistance sensors. So this wasn't actually done on an eye. This was done on an eye model. So we fabricated and designed a simple contact lens with small, tiny magnetic sensors that were both mounted on the lens as well as a glass frame in order to classify and find out where the eye is looking. And this was used in order to control a Tetris game, and further details also available. So our vision was to later on see how we could develop an autonomously driven platform, electronic platform that can classify gestures and also interact with the outside world. However, this work kind of stopped, as you know, because of the ethical approvals and also the difficulty in developing such a platform. So moving on to liquid crystals, which is what I believe the majority of yourselves are working on at the moment. So as you know, liquid crystals, they are at the core of the majority of our head-mounted display devices. So I've tried to classify where liquid crystals are used in these technologies, and this is very nicely also summarized in this reference, one of these fantastic references by nature. So liquid crystals used as LCDs in our augmented reality and virtual reality displays, LCOS devices. I used to work on these a long time ago, as well as planar optic devices. So the advantages of LCDs in head-mounted displays obviously is that mainly the cost is relatively low. Power consumption is also low, which means that the battery lifetime can be quite high. Problems with LCDs for head-mounted displays, as you know, the viewing angle is relatively low. We've also got the screen door effect. Sometimes we could see the pixels in these head-mounted displays. And because we're using liquid crystals, the response time is typically quite slow. Does anybody know what commercial examples of LCDs are out there? Anybody tell me? Any commercial examples of LCDs used in head-mounted displays? No? Yeah, so, no? What? So, what, VR or AR?
Yeah, definitely.
VR definitely, right? Yeah, so liquid crystal displays used definitely in VR. So examples like the Oculus Quest and the HTC Vive. In fact, the HTC Vive has not just one, it has two LCDs. Okay? And we've got plenty of these in our lab. So if you'd like to visit our lab, you're more than welcome to try them on. What about LCOS devices? Any examples? Anybody know examples of LCOS devices? Here we go.
No, well, no.
No. Anybody? Anybody working on head-mounted displays here? Who's working on head-mounted? Yeah. Okay, so have you heard of the HoloLens? Anybody heard of the Microsoft HoloLens? Yes, Microsoft's just around the corner, just down the street from here. Yeah. So the Microsoft HoloLens uses LCOS. So advantages, very high resolution, great contrast. It's a lot more expensive. And I'll touch upon cost of these head-mounted displays because this is something that we do in our group quite a lot. It's obviously a bit bulkier than traditional VR displays. Other examples where liquid crystal displays or liquid crystal devices and materials are used in HMDs is these planar optic devices. So holographic devices, holography tip. So these are used in order to improve things like the field of view of AR and VR devices. Obviously, the main problems, cost and brightness. Okay, so yeah. an example of our Microsoft HoloLens device. So why XR? Why are we interested in XR in Glasgow? Well, as I said, I'm quite passionate about teaching and learning. I really like this. And I think that XR devices are great devices, great tools to help people understand things better, especially when it comes to discovery. In order to make spatial relationships between things. If we look at the market for XR technologies, according to Statista and according to other sources in the literature, so obviously the biggest market for XR technologies is gaming, but second, just after that is training. So it's a fantastic medium to use for teaching and learning and training purposes. Huge market, in fact. According to experts, many of these experts, according to the literature, are saying that education is one of the areas, one of the skills, one of the areas in which people can learn better using XR technologies. And this is the thing that we are focusing most on. This is the area that we are focusing most on at the University of Glasgow. So some statistical numbers here. The main takeaway message is that there's a lot of investment going into extended reality, going up to possibly $100 billion by 2026. In terms of share, so still the market is mainly dominated by VR devices. So the vast majority of shipments are virtual reality devices. However, that's going to change very slightly towards 2027, within the next 3 or 4 years, where there will be more AR devices, examples of which obviously you've been seeing now, such as the Apple devices, such as the Vario XR3s, and so on. In terms of shipments and market share, so it comes as no surprise that Meta, the Oculus headset, has the biggest share of the HMD market. So if we look here at this time plan, this is quite interesting here, in my opinion. Does anybody know, so this is Q3 2020, Q4 2020. Why do you think there has been this huge jump? Why do you think there's been this huge jump? What happened here in 2020? Huh?
Lockdown.
Lockdown, yes, exactly, lockdown. So around this time, this was COVID time, right? Why do you think this is interesting for VR? Why do you think COVID might have an impact on VR and VR sales, and especially Meta? More people are obviously alone at home. More people want to feel, more people want to be entertained. It's a great collaboration, great social interaction tool. So Meta, Oculus capitalized on this quite a lot, yeah.
So is that just that the volumes of the Meta product increased 400% and everything else was about the same?
Yeah. This is really interesting. So that is one thing. The other thing is, obviously, so this is Q4. If you notice, usually in Q4s, Meta does really well. Yes, Christmas, and that's a fantastic time for people to buy the products, right? This is the holiday season. Meta does really well in Q4 generally, really well. So yeah. This is also coinciding with when Meta launched the Quest 2. So you had COVID, fantastic timing for launching of their new product. And also it is the holiday season, which is the perfect time for buying products, electronic products. And then look here as well, so all this 7%, and then another spike. And that was when Facebook changed its name to Meta. So again, an upsurge of interest around Q4 2021 again. This was October 2021. When Facebook changed its name to Meta. And then obviously that, so here, so as we've mentioned, sales usually during a holiday season. If you look at Google Trends, this is quite interesting. So here I looked into a comparison between the metaverse and virtual reality. And if you look at Google Trends, there was again this huge spike around Q4 2021. And this is exactly, again, the same time in which Facebook changed its name to Meta. Huge spike in demand, or huge interest in metaverse technologies, if you like to call it that. I prefer to use immersive technologies. So anyway, in terms of prices, so obviously Apple Vision Pro is one of the most expensive. I wouldn't say that this is the most expensive. There are more expensive headsets. So the Vario XR3, for example, very expensive headset. We bought one of those in our lab, but yeah, and great resolution. Quite heavy though. It's a tethered device, but in terms of its, in terms of commercially available devices, one of the most expensive in comparison to others out there in the market. Okay, so let's talk a little bit more about liquid crystals and what we're doing, and also what you folks are doing. So back in the day when I was doing some of my research, I was mainly interested in very simple. I thought, let's keep things simple. I like to keep things simple. So let's examine a simple liquid crystal material, homeotropically aligned. You folks know what homeotropic means, yes? Yeah, so homeotropically aligned material, that's vertically aligned material with a couple of electrodes at the bottom substrate, a couple of electrodes at the bottom silicon substrate. Very familiar, I'm sure, Tim. And then I was interested in seeing what happens when you change these dimensions, when you change the spacing between these interdigitated electrodes. And I tried to think of interdigitated electrodes, not pixels, and also the size of these pixels, the size of these electrodes. And I was interested in theory a little bit. My supervisor was also interested in theory at the time. And I wanted to see whether some of the theories that we were using at the time, such as the Landau-Digen's theory, one of those theories that we used to model liquid crystals. Anybody know what Landau-Digen's means? No? You guys are missing out. Okay, so very important theory for understanding how liquid crystals behave. And then seeing what happens when you apply a voltage to these electrodes. Okay, so when we talk about alignment of liquid crystals, there are really, just a handful of alignment techniques. Homeotropic, this is what I spent most of my time working on. There's also the planar, in which all the liquid crystals are aligned horizontally. There's the hybrid alignment, very interesting alignment as well, where you've got planar alignment at the bottom, or vice versa, and then, or planar alignment on one side, and homeotropic alignment on the other side, and then this in-plane alignment. And this is very similar in twisted nematic liquid crystal display devices. So part of what I did at the time was understanding defects. So these are disclinations. What happens when you have, so you're dealing with liquid crystals. These are materials that have both liquid and solid properties. So all these nice equations, they just tell you, basically, they're just a clever way of saying that in order for us to understand how liquid crystals behave, we use two main parameters. One is known as the S parameter. It's called the order parameter. And the N. N is the director. It's the average orientation of the liquid crystals. And if we wanted to model this, then we've got to understand how this material, there's an interplay of things happening in the liquid crystal. You have the electric field strain energy, as well as the bulk strain energy of the material. And there is this interplay between these two parameters that we have to optimize. And we use Euler-Lagrange equations in order for us to optimize this energy. We try to find the mean free energy. minimum mean free energy. Okay, so these simulations, these are finite element simulations that show how the liquid crystals deform as a result of applying this electric field due to these electrons at the bottom. And I was interested in seeing what happens when you increase, when you change these voltages in such configurations. So we did a bit of work on this, and it was interesting because it led us to understand alignment of liquid crystals as a result of applying these fields. And how these disclinations move. This is obviously something that you cannot see. You can only, when you're characterizing a liquid crystal cell, most often you're characterizing it optically using a microscope. So you could see a disclination line, but you cannot see the details. And there's a lot of information that you can get out of these simulations, such as the nucleation of these defects and the movement of these defects. And we spent a bit of time understanding these defects, and some of this work has been published also quite recently. Yeah, so just showing you some of the work that I did back when I was in Cambridge. I used to use this electron beam writer for fabricating these cells. Spent a lot of time passing such equipment, and also marveling at how someone, can develop such a tool. This was someone's PhD project, by the way, this electron beam writer. I noticed that you folks have published a research paper, an interesting research paper that looks into the alignment of crystals using these grating structures. So this was something quite recent. Mike, in fact, you're one of the co-authors. So almost 20 years ago, Mike, we did something similar here in Cambridge.
Good job, man.
Yeah. Oops, sorry. And Tim's obviously involved. So this we were looking into, because just as you had looked underneath the microscope and observed that for different grating structures you get more light being observed underneath the microscope. While I was experimenting with my cells, I observed something similar. Like I say, I was also interested in seeing how the liquid crystal behaves as a result of these electrons. So these are some of the samples that we developed. And, I went down to 100 nanometer interdigitated electrode structures. And I was also, just as you were observing for different gap widths and different grating periods, I was also observing an increase in the amount of photo-generated current. So having a bit of a theoretical background, I was trying to relate the strain energy to what's happening in the liquid crystals. So the alignment as a result of strain energy. And as you can see, by decreasing your electrode spacing, you're straining more of this material. And here, so these were tiny structures. I believe these were 250 nanometer structures that were separated by 1 micron gaps. And as you were orientating your sample, you could observe a greater amount of light being reflected. So this was a conference paper that we published. We didn't really follow it up. We should have done so, but that was a long time ago. And at the time, I was trying to correlate things at the same time. I was trying to correlate. So Berriman had an interesting theory in the 70s. He was trying to relate alignment of liquid crystals due to grooved surfaces. People say that alignment is more of an art. Yeah, it's difficult to understand alignment of liquid crystals. But Berriman, I think, was one of the very first people that discussed perhaps this issue of topological alignment due to grating structures. And there I was trying to relate Berriman's theory, Berriman's equations to what I was seeing from my simulations. And I could see that there was a similar trend, albeit that different scale. Anyway, very interesting. This is something that perhaps we could pursue together later on. So yeah. Currently in our group, we're also looking into how we could use liquid crystals for other applications, including antennas. So here I'm showing an example of an antenna that is embedded on a lens, right? This is a contact lens, and we are here proposing the concept of integrating these antennas onto these lenses and using materials like liquid crystals to tune the passband of these lenses. So this has a variety of applications. Could be used for telecommunications applications, could be used for others as well. So here we could see that there is, we could tune this material's passband as a result of applying an electric field to these interdigitated electrodes that are placed on both the bottom and top substrates of this material. We took it a step further, and here we're interested in these extended reality devices. Here we're now dealing with cholesteric liquid crystals, and we're seeing the impact of. There's a lot of material on this slide. I'm trying to show as much as possible and little amount of time that we've got. But here we're showing that for these cholesteric liquid crystal materials and for different chiral dopants, and by applying different temperatures, we could also switch between different modes. So transparent, VR, and AR modes for different chiral materials. Yeah, for different materials. So we can tune the passband of the material using different chiral agents, different chiral dopants. And not only that, and so you've got to the experimental results matching our simulation results. Yeah, so this is very reassuring. We've got a very nice match between both of these. But in addition to that, by varying the temperature as well of the sample, we could also go from transparent to AR mode, transparent VR, AR mode for different colors of RGB lasers. So that was some of the liquid crystals work that we're currently pursuing, and also what we previously did. In terms of teaching and learning, and this is just an explanation of how my interest in teaching and learning, how it all started. Well, this was thanks to a collaboration that the University of Glasgow developed with a Chinese university, with a partner based in China, where they were looking into developing partnerships in certain programs. The reason why I'm bringing this up is because it was very difficult at the time to try to deliver these teaching materials remotely to students who are based abroad. So not just myself, but also my colleagues, we looked into our curricula and we tried to see how we could deliver materials concisely and effectively to our students who are based in China. So we explored the use of technology. We looked into the signature pedagogies of a discipline like engineering. So engineering, the way that it's taught traditionally, it involves someone just as myself standing and just delivering information. It's one-way communication. There isn't a lot of interaction, unfortunately, even though engineering is a subject that involves a lot of practical work. It's an apprenticeship subject. You don't do enough of it. So we thought, let's dive deeper into the signature pedagogies of engineering, understand what really works for engineering. So engineering is known for things like project-based learning, team-based learning, and we tried to integrate these teaching pedagogies into our curricula and include technology as well at the same time. So we experimented. We had a number of modules to deal with, and we tried to integrate these modules or the concepts, the core concepts, threshold concepts in each of these modules into one module that we called Team Design and Project Skills. And it involved students developing a rover, right? And the rover had to accomplish a few technical tasks. And we designed these tasks so that students had to learn as much as possible from their degree programs. And the result was really extraordinary because we were able to teach students the principles of design, this circular engineering design process where they've got to start off with defining a problem, define what your criteria are, brainstorm solutions, develop an experiment, test the prototype, evaluate the results, and then to report and to communicate the results to the outside world. That's really what engineering is about. We also, in an indirect way, taught them how to deal and how to communicate this data amongst their colleagues. Engineers rarely work in solitude. We all have to work in teams to develop products. I'm not aware of any product that was developed by a single person. And so if you're working remotely, how are you going to share that information amongst your team members? So we explored what technologies can be used in order to facilitate the communication of this information. And at the same time, since this is a module that was assessed by students, we wanted to make sure that everyone's contributions mattered, right? And there weren't just a few students who were carrying the entire project. Okay, so a case study. This is a video that demonstrates what some of the teams managed to produce. I'm only here showing one team's results. This was before COVID's time, but you could see some of them, you know, this is all edited by them. They would develop this video themselves. They developed the robot themselves. They were able to accomplish all the tasks with minimum supervision from the instructors. Okay. So in terms of sentiment, it was also interesting to see how this project was received, or how this module was received by both Glasgow students or students in the UK in comparison to students in China. So when we issued a survey to understand sentiments and people's and students' behaviors, so we had some interesting and contrasting results. Just to pick on that and to be brief. So for example, things like your preference to working in a team. So in China, the vast majority of students do prefer to work in a team, surprisingly, whereas in the UK, no, we would prefer to work individually. Why should we work in a team, right? In terms of splitting up the work, our approach to splitting out, arranging our groups, similar sentiments, and in terms of whether they would like to, to work and to help others, then again, very similar. Okay, so I've mentioned that our delivery method was obviously remote. Some of our students shared with us ideas how we should communicate with them. Okay, and there were some interesting results that were generated as a result of this. So for example, for those of us who are teaching academically, students really do appreciate supervisors who are able to respond rather quickly. Okay, so if you want good feedback from your students, you want good reviews from your students for courses that you're delivering, make sure that you do give them quick feedback. Something else that they also mentioned was, regular feedback was important. And as you can see, when it comes to faculty members or staff members being liked or being popular, it's really the main attribute is their responsiveness to questions. So students really like to faculty members who do reach out quickly and respond quickly. So how do we achieve that in a remote environment? So we thought about the different tools that are available, and in a nutshell, what we came up with, in order to facilitate the communication between students and also supervisors, why not encourage the use of electronic laboratory notebooks? Anybody heard of these? Any chance? No, nobody's heard of an electronic lab notebook? Okay, so what do you use usually for recording your results? Or do you not use anything?
In the undergrads use something like that.
Yeah.
In the programming, I use chapter.
Okay, fantastic. Yeah, so definitely. Okay, so you do use something. That is fantastic. So when I was at IBM, we had to use something and it had to be signed as well. Okay, so we trialed a number of these notebooks. Some of them were more successful than others. And yes, so some of the note-taking tools were very popular amongst students. So OneNote, for example, was highly rated because of its ease of use, right? And it was also in terms of, not just in terms of ease of use, but it also facilitated collaboration. And again, I want to stress the fact that engineering is a collaborative subject. So we needed to use tools and encourage the use of tools that facilitated this collaboration. So things like, for example, developing these systems. So imagine if you have to work remotely, or you have to work with a team of people who are in different locations. How can you develop a system like this without collaborating effectively? Moreover, how can you develop systems? How can you design systems effectively that are going to cause this paradigm shift in people's perceptions in using renewable energy, right? If you're going to design these systems using conventional two-dimensional tools, things like if you design solar energy systems, things like Polysun and PV-Sys and others. So that's why I think that the future designing these systems has to be done in an immersive environment. Yeah. So this is where we believe that in the future, instead of designing systems using these two-dimensional screens, in the future, we'll be designing our, for example, renewable energy systems in an immersed environment where we can collaborate with others, where we can feel that we are physically present in the environment in which the system will be developed. And I think that's the best way, the most effective way to design a system, such as, for example, a solar energy system. Now, all these folks, when they're designing software tools, they rely on surveys. Yeah, so that's how that's the main method in which they evaluate the effectiveness of their tools, using surveys. However, surveys are prone to bias and error. You have to force the participant to reimagine how they felt in that experience after the experience has been completed. So in our group, we thought, okay, so that's not much use to us. Why don't we use sensors? We're good with sensors. So this is the traditional way of collecting feedback. It involves, you know, getting ethical approvals and asking students, begging students to complete your surveys on time, and continuously reminding them to complete their surveys. So we thought, why not get rid of that and use instead sensors? In this case, we've got real-time data, live data from participants to understand how they really feel, how they behave. And we've got a variety of sensors that we use in our labs, such as EEG, ECG, all the kinds of Gs that you can think of in order to collect feedback from our participants, okay? We've also got eye trackers, our own lab-built eye trackers, as well as commercial eye trackers, again, to understand where users are looking when they are designing systems, either two-dimensional systems, systems using two-dimensional screens, or 3D systems as well. And that gives us a lot of useful information from participants. We've also explored the use of, so we are fusion guys. We like to use a variety of sensors. So we've also explored how radar can be used in collaboration or in partnership with other sensors to understand user behavior. And you could see here an experiment in which a participant was designing a solar energy system using a two-dimensional platform such as Polysun, in comparison to designing the same system using immersive virtual reality. And we can get a lot of data about engagement and cognitive load this way. So here is an example of a system that was developed, or an experience that was developed by one of our students in the group. So here, this is showing how you can start to design a system very quickly. So instead of the two-dimensional method, here you've got access to a room. You've got the various components, such as, for example, your inverter, placement of these components, your charge controller. You've got a sense of scale, where it would fit, batteries. Next, you will go onto the roof. You could then move these panels on top of your roof and get a visual idea about, as a result of moving these panels, changing the tilt angle, how much energy can be generated as well from the roof, and by increasing the number of panels and so on. So it's it's an easier method. We're really democratizing the process of designing these systems instead of limiting it to a few people. In terms of collaboration as well, since we're being on that, we did again another experiment involving a physical collaboration using Lego. Okay, so designing and building something using Lego, and then comparing that, the same task, it's in virtual reality, again, people immersed inside different environments, and again, we felt we managed to get very similar results in terms of being immersed, getting the sense of physical presence. So, we tried this with other students internationally as well. So this is another project that was funded by the British Council, in which we tried to advocate the use of virtual reality to promote understanding of the UN Sustainable Development Goals. It was very well received. Here, students were able to design their own environments that demonstrated a better understanding of what these Sustainable Development Goals are. Over a very short period of time, they were able to design these immersive environments. This takes usually quite a lot of time, but because they were in teams for a short amount of time, they were able to design these games and environments independently with very minimum supervision. Also in Glasgow, ran something similar. There was another course where we wanted to integrate sustainability in our modules, and here students were encouraged to design environments that promoted one of the UN's SDGs, one of the UN's Sustainable Development Goals. And surprisingly, all 17 SDGs were covered by the students. All of them were covered by the students, some more than others. So this showed representation of which of the SDG students wanted to focus on. And here, similar to a real world environment, students were asked to present their ideas to a board. Okay, this was a group of investors, people who were from industry. A few contacts that we used to know from industry were invited to sit in and to listen to presentations by students. So an example of teaching, and students produced some amazing work. So for example, here, some of the students, they wanted to focus on gender equality and understanding female issues. So one of the themes is to raise awareness about how females feel when they're walking and in their daily lives. Others wanted to raise awareness about safety on the roads. Others wanted to raise awareness about using public transportation, and so on. Yeah? So a lot of projects that were developed by these students. So, yeah, so there's a conference that we're also organizing in Glasgow, and I'd invite you all to contribute and to visit Glasgow and to attend this conference. So this will be focusing on immersive learning. So the conference will take place in June. You're very welcome to visit us and to take part, where you will also explore and learn more about what we are doing in Glasgow and beyond in immersive learning. So that is very close to, that is in fact the end of my presentation. As I say, I tried to showcase some of the work that we are doing in this area. Hopefully there will be opportunities for us to collaborate, but just like to thank you all for your attention and also for the invitation to deliver this presentation here in Cambridge. Thanks again, everyone.
You have any questions for Professor Ghannam?
So you mentioned in terms of like the measurable feedback you have, it's mainly based on sensors, but I'm guessing now with other learning algorithms, like you have computer vision, you have, facial expression and identification, which doesn't sort of like introduce so much hardware overhead in terms of the sensors. So how does the performance between like these commercial like programs and that you use?
Okay, very interesting question. So the question is around the use of non-invasive techniques, such as, for example, facial recognition techniques in comparison to wearable sensors. So that is something that we are also looking into. Now, the problem with the image recognition techniques is that how could you do that with a classroom? How can you do that over a classroom environment? So it was a little bit more difficult to obtain that kind of feedback over a big number of participants. Also, image processing techniques have their limitations. You're not able to get the nuanced feedback in comparison to wearable sensors. Especially also when you are in this virtual environment, the main method or the main feedback that you can get from image processing techniques is the eye tracking data. But things like, for example, heart rate, pulse, cognitive load, these things you cannot obtain from image processing techniques on their own. So we wanted to get as much information as possible, and that's mainly possible using these wearable sensors, unfortunately. Thanks. Yeah, excellent question.
Question? No, if we have no more questions, I will just mention one thing. This is the 47th Cape Advanced Technology Lecture since 2014. It's actually going to be the last one, but we've had a great series of talks. And before that, from 2006 to 2012, there were 203 Cape TRKC technology lectures. So this is actually the 249th in the Cape sequence. So a very fitting ending for the Cape lectures. So thank you very much, Professor Ghannam, for your talk.
Thank you so much. Thank you, Mark. Thank you, everyone.